Hello everyone, and welcome to this presentation on collapse, advanced and fast statistical computing and data transformation in R. I'm Sebastian. I'm the main developer of Collapse, and I'm currently a junior researcher at the Kiel Institute for the World Economy in northern Germany. So this presentation was originally made for the user conference, but I'm now recording this talk post the conference because unfortunately my conference talk has been overshadowed by some connectivity problems. But to be honest, I'm also happy that it went that way because this is really a seminar style presentation where I introduce the computational architecture of Collapse in some measure of detail, and I also show you a bit how I use Collapse in my research work, with the hope that will inspire you also especially if you're doing economics or social science research, to really utilize the computational capabilities that Collapse adds to R. And I didn't feel that was possible really to do in 15 minutes. So I'm happy about this opportunity to record this now post the conference. And I'm going to take just a little bit more time. So in terms of the outline, I'm first going to just give you a broad overview about what Collapse is and what it offers to R. And then I'm going to talk a bit about the core statistical infrastructure of Collapse. Talk a bit about the data manipulation functions. Then I'm going to walk you through an example involving OpenStreetMap from my own recent work. And then I'm going to talk a bit about the time series and panel data infrastructure that Collapse offers, and also a bit about the API extensions, particularly because that could be a bit confusing to new users coming from other packages. So to jump right into the presentation, what is Collapse? So if I would break it down in one sentence, I would say this: it's a C and C++ based R package that really facilitates statistical computations of high complexity in R. And it does that at very outstanding levels of performance and programming efficiency, and also in a way that can really be integrated seamlessly with popular classes and data manipulation frameworks, such as Tibbles or data tables, SF data frames. And it also fully supports the efficient infrastructure available in base R, in particular matrices, which are frequently underutilized in popular data manipulation tasks, although they are a very efficient data structure in base R. So to give you a bit more details in terms of some bullet points. So Collapse is really an infrastructure package for R, and it provides first and foremost a very large set of statistical functions and operations that are fully vectorized along multiple dimensions. In particular, they're vectorized across columns, and they're also vectorized across groups. And this includes vectorizations for weighted statistics, like weighted means, medians, modes, and so on, and statistics for categorical data, which includes the mode, it includes group level distinct value counts, first and last values, and so on. Collapse also supports some really enhanced time series and panel data support, including the ability to index both time series and panels with multiple variables that identify the individual and time dimensions. It has advanced transformations such as scaling and higher dimensional centering of panel vectors in particular, and also some advanced exploration tools such as panel data autocorrelation functions and panel decomposed summary statistics. It also features some recursive operations on lists of data objects, which is not really going to be focused on in this talk, but there will be one example where you see where this infrastructure comes in and where it is also necessary to have this kind of functionality. And it also has some advanced descriptive statistics tools, in particular very fast summary statistics, detailed descriptions of data frames, cross-tabulations, and so on. Yeah, which I also won't really talk about in this course, and which is also quite easy to understand. It also has some data manipulation, programming, and utility functions, including quite fast routines to group and order data and to determine unique values. And the most recent addition really to Collapse is that it supports data transformation by reference, so without making a copy of the object in R, and it supports OpenMP multithreading in multiple statistical functions now. And these two areas will really be extended in the coming months and years to really be a substantial part of the infrastructure. What is special about Collapse apart from the infrastructure it provides? Well, one of the big points to me is that it's really a class agnostic framework. So it means it basically supports all classes that exist in R, or let's say all classes that contain data and that are pretty popular as a format to deal with data. That includes all the objects we have in base R, like vectors, factors, matrices, data frames, and lists. But it also includes very popular further classes like TS, XTS, data table, Tibble, as simple features, panel series and data frames. Yeah, and it can also be used with some specialized classes like tsibble, at least in the sense that it preserves the data structure, although it doesn't really integrate with the functionality very well. And this is done really through, sometimes through S3 methods, but also through some, I would say intelligent ideas on how attributes of objects should be preserved in computations. Collapse is also extremely fast and efficient, and particularly the C++ based infrastructure of Collapse allows computations to scale near linearly in time for almost all computations. And this speed is really not dependent on the number of columns or groups a problem might have. So the data size is really more important than the number of columns or groups. And the reason for that principally is that group computations in Collapse are performed as a side effect. So I don't really iterate over groups for most of the statistics, but there I iterate over observations, and the grouped computation really happens as a side effect. So the whole loop basically is grouped. And that is quite different from the way most other data manipulation packages work. It also has some very highly optimized R code. In particularly, I only use primitive or internal base R functions, and I outsource most checks on data objects to the C++ level. And I also try at the C++ level to provide infrastructure for all R types, like integers and doubles and strings and so on, so that there are really no conversions moving between R and C++ in Collapse. And that allows you to have a very efficient infrastructure where I would say all functions execute below 50 microseconds on a typical computer. And that really allows you to write programs in a different way. There are also many internal optimizations in Collapse, and particularly for strings, factors, integer and logical vectors where there's no missing value, singleton groups, so groups with only one observation, and pre-sorted and unique data where I try to do as many optimizations as possible, knowing what I have, what the characteristics of the data are that go into the functions. And the final performance feature I think about Collapse, which is cool, is that I really want this to be a programming framework so users can access many C++ level algorithms, helper functions, and also the core S3 methods, say for vectors, matrices, and data frames directly. So everything that is useful basically in terms of algorithms can be accessed by you and used for programming. Collapse also has a quite stable API. Since at least a year or so, it's very stable and also very flexible. It supports standard and non-standard evaluation. And most functions, you can input vectors or matrices and data frames, and in that sense it's very flexible. We also have some function shorthands, and another feature that was recently added in Collapse 1.7 is that there's a flexible namespace with a global option that can be set to basically mask some base or dplyr functions with the collapse pendant, so you can speed up basically existing code by substituting collapse functions without having to do any kind of rewrites. The final point here I want to make is that Collapse was really designed from the very start to deal with socioeconomic data, which is data where there's typically an abundance of missing values. And for that, the default across the whole package is to remove missing values, or better, to skip them at the C++ level in a very efficient way. And I also try to reduce the statistical artifacts that a base R, as it is right now, generates from, say, computing on groups where you have only missing values. And there you usually get some statistical artifacts like infinite values or nans or so on. And I try to reduce that in Collapse. And Collapse also supports variable labels and other attributes attached to columns, which is something I also think is necessary when working with socioeconomic data, that those attributes basically are not dropped unreasonably in a computation. So to jump into the framework, the main, or one of the core parts of the framework, is really a new set of statistical functions for R, which are S3 generic, and they typically offer much greater performance and also flexibility than base R. So the names of these functions are contained in this global macro, which is just a global variable in the Collapse namespace .fast_stat_fun here. And you can see we have 14 of these functions, and they all are S3 generic with a set of methods. The default method for atomic vectors, we have a matrix method, we have a data frame method, we have a method for grouped data frames, and we have a list method, which is basically works just like the data frame method, but it allows you to use them also on unclassed data frames, which can be a more efficient way to manipulate data frames. So here I give you some basic usage examples, just calling the fast mean function here on a vector, on a matrix, or on a data frame. And you can see that these functions by default just work column-wise. They compute the statistic on each column of the data. And you can also see here, if you know this air quality data set has some missing values, and these are automatically removed because the default is to remove missing values. And here you can see some basic benchmarks. Here in the first case, I just have a random normal variate with 10 million observations. So you can see here that the fast mean just in the default or just in serial mode is about twice as fast as the base R version. And if you use 4 threads, you can really get a substantial performance improvement. And with matrices, it's the performance, I think, similar to the base R, efficient base R functions like call means. And it's much faster computing statistics on data frames. And of course, it's also more convenient because you don't need to call an sapply or lapply to apply a function to a data frame. You can just call the function on the data frame and it will compute on each column. So on the bottom here, we see a data set where we have about 5,000 rows and about 11 columns and some missing values. And you can see that, it's about, here almost 6-7 times faster than base R without any multi-threading. These functions, they're not limited to these kind of simple computations. They can do much more, actually. So this is the syntax of the typical function. of a fast statistical function, and you can see, first of all, beside the input x here, which can be a vector matrix or data frame, they have a g argument for grouping. And this can be any vector or list of vectors to define groups over which the data should be aggregated, or it can be a group object, which I will get into a bit later. There's also, for all functions where this makes sense, there's a weighting argument, like for the mean, for the median, for the mode, and so forth. There's a weighting argument even for sums and products and so, because it can be sometimes more efficient to do the weighted computation instead of pre-multiplying the data with something. And then there's also a transform argument, which allows you to transform the data directly with the statistics you computed on the data. And then again, there's the missing value removal, which is true by default, and then some other arguments to either use names from the grouping variables as row names or names, or you can drop dimensions if you have a matrix or data frame which will return just a vector if you don't do any grouped or transformed operation. You can set a variable number of threads. The default is 1, which actually calls also a serial version of the code in some functions, so there's no really overhead to multi-threading being available in these functions. And there's some arguments that can be passed to try. In particular, there's a set argument that allows you to transform data by reference. But I'll get into that a bit later. So here, I just show you some basic examples. First of all, we can compute just a weighted mean, also with fmean, which is exactly the same, gives exactly the same result as the built-in weighted mean function. And the specialty here is that Collapse generally also supports missing weights, which base R doesn't support. And these missing weights, they're basically treated like zero weights. So it means that the observation is just skipped. It's not counted. And this can actually also be a way to just compute a statistic or efficiently compute a statistic on a subset of the data. If you just say pass a logical expression to the weight argument, it will just compute a statistic on the subset of the data by just skipping the computations for the missing weights or for the zero weights. And then there's the grouping function here, where we just compute over species here of the iris data set, which should probably be well known to you. This is obviously much faster than tapply, especially for larger data. This also works with data frames. Here I'm taking the first 4 variables, the numeric variables of the data set, and computing a species-wise mean. And it also here works with the grouped data frame method, both using a built-in collapse verb, fgroupby, which works very well with these functions and very efficiently, but it also works with the dplyr version, which where there has to be some internal conversion of the grouping object, which is so it's a bit less efficient than that, but it works. We can also do weighted group means, if the weighting variable is a part of the data frame, so this expression here just adds the W as a column to the iris data set, and then we can group by species and weight here the mean, and this by default will actually compute also the sum of the weights, so that you could use this for further computations. But it would drop. You can also omit this if you put the keep weights equal to false in the fmean call here. So all of this has fairly little overhead, even at the micro level. So this here gives you basically a micro level benchmark of this computation on the iris data set. And you can see just using lapply here with the base R weighted mean is slower than using either grouped or weighted computations with collapse. Now, what is probably more interesting to you is this benchmark down here, where I have 10 million observations and I have 1 million random groups. And I'm comparing here collapse against data table, where I'm just using a serial version of data table for M1 Mac. So there's no overhead to there being multi-threading here, because it's just serial. It's just running on one thread and was compiled serially. And I generate the data table with X, which was 10 million random normal variates, and the G, which here has 10 million 1 million groups in a random order. And I set the key here on G, which means I pre-group this using data table. And I do the same thing with collapse, which is this expression where I just turn G here into a collapse grouping object. And then I do this micro benchmark here, and you can see that the first expression is just the simple mean of collapse over those 10 million observations. And that takes about 9 milliseconds. And if I do the grouped mean, so if I do this in 1 million groups, it's just a little bit slower than that. And that just is the case, or it has to be the case, because I have to allocate a results vector of 1 million observations. And then I have to do 1 million divisions by an integer, where the group counts are actually contained here in the grouping objects, which is an additional reason why this is very fast. And if I add the weights, then it goes up a bit further, which is also has to be the case because I have to allocate 2 vectors and some of 1 million observations and sum the weights, and then I have to do 1 million floating point divisions, dividing the sum by the sum of the weights. So this adds a bit, but you can see that this is overall faster than the data table infrastructure, which basically loops over those groups. And of course, data table can be parallelized at the subgroup level, which is a great advantage if you have very large data. Say you have 1 billion observations and you have 100,000 groups, then you want to have something like a subgroup level parallelism. But if you have an abundance of groups and you have data that is not so huge, and in particularly if you have multiple columns in your data, so that you could also apply a parallelism over those columns, then the architecture offered by collapse here, which performs grouping basically as a side effect to a single loop that iterates over observations, can be substantially faster than data table. And I'm going to show you that a bit later with an example from my work. So collapse also really has this missing value removal equal to true default, and there's also some effort put into dealing with groups, say, that are all missing, or when there's only missing values in a vector. And in that case, collapse just returns a missing value in all functions, whereas in base R you get a lot of statistical artifacts like infinite values for the min and the max. You get zeros for the sum, or you get a 1 for the product, or an n for the mean. Which I think is something you have to typically deal with ex post, which is not very useful. And I'm just giving you an example here from the Stata software, where you can see that it works mostly also like collapse works, except for the sum. And I've actually, I'm planning to add an argument to this fsum that allows you also to get zeros here, because I do think that makes sense in some cases for the sum. But in generally, in the default setup, collapse very consistently just returns a missing value. So you don't have a lot of statistical artifacts in your data upon aggregation. And another concern that really annoyed me was base R. If you look at dplyr here, you have this data which has variable labels attached. And the base R statistical functions that just drop it typically. And collapse really is more conservative. It will only drop attributes of your columns if the data type is a different one upon aggregation. And there are certain exceptions like time series objects where it does not make sense to attach the attribute if on to an aggregated object. But otherwise, collapse is very conservative, so you can you can expect your data to look the same and have the same structure upon aggregation or any transformations that where it's not reasonable to assume that it destroys the structure of the data. So now I want to go a bit into the transform function, which is an argument to the fast statistical function, but it's also a standalone function really that can be called by itself. And it's basically an enhanced version of sweep for grouped. It does not have to be grouped, but usually it's grouped, replacing or sweeping out of statistics. So you have X here, which is the data. Stats is the statistics. You have a function to sweep the stats out of X. And you have a G argument where you can do this by groups. Yeah, so stats could be a vector or matrix whose elements or rows correspond to the groups. And the groups needs to be a vector matching the length of the data. And all of this can be done by reference, which means it will modify X in place. And we have 11 different operations supported. Here we can basically impute the missing values in the data by just replacing the missing values with the statistics. We can just replace the entire data with the statistics within groups, or we can just replace the non-missing values in the data with the statistics and preserve the missing values in X. And we can also do a lot of other popular operations like centering or subtracting the statistics, dividing, computing percentages, adding, multiplication, or even computing the modulus. So this function can be called internally from the fast statistical functions. If you remember, it's just the fifth argument here, or the fourth argument to most of these functions. So we can pass here a transformation, or we can alternatively first compute the aggregate statistics and then call the transform function. So these two calls here are perfectly equivalent. They both do a grouped and weighted centering task. So we center X on the weighted group means of X. These two are equivalent. And we can also do this by reference. So these two are also equivalent, and they would do this by reference. So without creating it, they don't return a copy of X, they modify X in place. And you can see that both of these options are significantly faster than base are here using the averaging function from the stats package. This will also be even faster on larger data. So here I'm just showing you or giving you a glimpse of what this flexibility built into the statistical functions can mean for your data transformation possibilities. So here I'm just here inserting some missing values into the iris data set. And here I'm just imputing the data set by reference by species wise median. Yeah. So I'm computing the median for each species, and I'm just by reference filling in those missing values with that median. So this call doesn't return anything. It invisibly returns the iris data set or the numeric variables from that data set, but it will just have imputed those missing values by the median. The fact that we can pass vectors or lists of vectors to the grouping argument and different transformations to the transform argument means that in a single call to transform on this data frame, or f-transform, which is a faster version, we can do operations using several different groupings at the same time. So we can compute here percentages of the MPG variable without any grouping. We can compare MPG to a grouped median of MPG by cylinders. We can do another median computation using a centering task where we group by VS and AM, and we weight by this other variable here. And this here is a call where we compare the mean of MPG aggregated over two different groupings. Here we aggregate over VS, here we aggregate over AM. And you'll see we have left the weighting slot empty. We're not using any weights. As you saw in the AP or the description of the transform function, we can also use an integer to indicate these different transformations. So here I'm just using one, which is just replace fill. So I'm just replacing the data with the statistic, and I'm making a comparison between these two. And you can see the output is logically here. Collapse also has some arithmetic operators based on the transform function, which are more convenient and also faster than base arithmetic, in particularly on matrices and data frames. So this just divides empty cars by empty cars, which will take each column from these two identical data sets and divide them. So you get a data frame of ones here. And this row-wise sweeps the median values of the empty cars dataset column-wise out of the dataset itself. So this is basically a median-centered version of the empty cars dataset. Now, as you saw, the G argument can process any vectors or list of vectors defining a grouping, as we've seen here. We're using vectors, lists of vectors. You can also use a data frame and so on. But grouping is a relatively expensive operation because it usually requires creating a hash table of something or ordering something. Collapse comes in here by giving you the opportunity to optimize repeated grouping. And for that, Collapse really exports all its algorithms for grouping and gives you also a convenient user interface for that. And the main function really to group data is called just group, grp, and it returns a list-like object of class group. So the class is the same as the function name, and that can be efficiently passed to the G arguments, or some functions also have a by argument. To basically give you a zero-cost input or a way to outsource grouping. So this is the syntax. So if X is a vector, it will just group it. If X is a data frame, it will also group it by all columns, but we can also select which columns we want to group by using the by argument here. And then most notably, we have an option to either sort the grouping in alphabetic order, or we can not sort it. And not sorting is typically faster, although the default in Collapse generally is to give you sorted groupings. So here I give you an example of the iris dataset where I just group this by the species column, and then I print for you this object, which just shows you it's a grouping object of length 150. So this is the data length, and it has 3 ordered groups. So the ordering is because we have here sort equal to true. And then it also gives you information about whether axis or the species column here is actually pre-sorted, and this is actually the case here. So it also says that this one is already sorted. And then it gives you here the group sizes, or it gives you some summary statistics of the group sizes. Now, just to give you an idea of how this object actually looks like, so it's just a list of 9 elements which provide inputs that are really necessary to perform various kinds of operations at the C++ level. So the most important ones here are just the number of groups here, which is 3, the group ID, which matches every row of the data to a certain group, and we have the group sizes. That if you recall, for example, if we calculate the mean without any missing values, we can just use those group sizes to divide the sum of the data over these IDs, basically. And then we also have the groups, the unique groups, and some information about whether the grouping is sorted or the data was initially or the grouping is ordered, which is if sort is equal to true in the group function, or whether the data is initially sorted, which is also true here. And then we also have an ordering vector, which can be used for more complicated kinds of computations where we indeed need to iterate over groups. So here you see just some examples. We have this object, and we pass it to the fmean function on the numeric variables of iris, and you can see it gives exactly the same output as we had before when we just used the species vector here. But this is much more efficient because there's no grouping happening here, and there's some elements here, for example, the group starts argument, which gives the first positions of the unique values by groups in this data set, can also be used for optimizations. For example, if you call f first, which gets the first values, and you put NA remove equal to false, this will just simply do a data frame subset using this group starts attribute. So this would be extremely efficient if you just want to break down a large data set by groups. Now, how can we use these grouping objects efficiently in analysis? Here I'm giving you an example from my own work on global value chains. And here I'm using the EORA 2021 Global Value Chain Database, which I decomposed using the decombar package. And this basically maps the structure of the world economy between 1990 and 2021. And it provides basically large input-output tables. And in this case here, I have an input-output table which has 188 countries and 26 sectors. And it's a square matrix basically, which has 4,888 rows and 4,888 columns. And so I have this for all these years, and this just shows you the output for, or the matrix for 1990. And I have two objects that I'm using from this list for 1990. I have VB here, which is a value added shares matrix. So it provides in each column, or each column corresponds to a country sector, for example, Afghanistan agriculture or Afghanistan fishing here. And the column will show the proportion of value added in the sector from all other countries and sectors. So the first number here is basically the value, or the proportion of output in Afghanistan agriculture, or the proportion of value in Afghanistan agriculture output that is provided by the sector itself, or and that is about 89%. And you can see that a very small proportion of the agriculture value added is provided by the Afghanistan fishing industry. And so you get the value added from all other countries and sectors here. And then we have an output vector, which is just basically the gross output of all countries and sectors in 1990. So this matrix, and together with the vector, is about 200 MB of RAM. And this here just shows you that this is indeed a value-added shares matrix. So if I take for all the years, just take the matrix and I sum along the columns, and then I just take the mean of all the rows, you can see that this is 1, which shows you that all the shares sum up to 1. Now what I want to do with this data here is I want to aggregate this because for my particular analysis, the country level with 188 countries is a bit too detailed. And I want to actually look at some world regions like Africa, Latin America, and so on, Asian, China. So I divided the world into 11 regions, but I'm keeping all the sectors. So I have here some region codes and sector codes, which I combine, and I create a group object, which is called RSG here. And you can see here that, this object has the lengths of the rows and columns of this matrix, but I'm aggregating this to 286 groups, which will be the region and sector groups. For example, this is here South Asia, so South Asia agriculture, South Asia fishing, and so on. And in the same way, you have other regions interacted with the sectors. So we have 286 groups here, and we have a list again of 32 matrices of dimension 4888 times 4888 for each year. And I want to aggregate those now. And I can do this here using an lapply call over this list of matrices. And I can take the value added shares matrix and I can simply sum by the groups over the rows, basically. So the rows can just be summed up because they are shares. And here I'm actually using 4 threads to do this, and I don't remove missing values because this is not necessary here and gives a small improvement. And then I can transpose the result, and then I need to aggregate the columns, which are now the rows of the transpose matrix. But because these are shares along the column dimension, this cannot be a simple sum or mean, but it has to be weighted by something to make sure the result is shares as well. And we can weight this simply by the output vector to make sure that the shares from different columns are weighted correctly. So this basically takes a mean of the columns weighted by output. And I'm also doing that with 4 threads. And then I'm transposing again to just make sure the aggregated matrix has the same results as the original one. And you can see that this whole expression here, this whole 32 matrices, about 5.7 gigabytes of RAM, aggregation took about 0.33 seconds with collapse. And this is very, very fast because to aggregate all of these matrices, I calculated it was necessary to compute 44.7 million sums, 2.6 million weighted means. And of course, you have to transpose things in total 64 times. And you also have to have 64 initializations of the thread parallel aggregation, which also adds a bit to the execution time. But notwithstanding, this just took 0.33 seconds on this M1 Mac computer. So it's really a level up in terms of what you can do in R. And this just shows you the result of this, just checking again in the same way that the shares add up to 1 for each year, and they do. So this worked very well. Now the final thing that you may want to do is to, once you have like an aggregated list of matrices, you might want to turn this into long form, like a data frame, to facilitate further analysis. And Collapse also provides you tools for that, list processing tools, and particularly the unlist to data frame function here, which allows you to really turn this list of matrices into a list of data frames, taking the year, which is the names of the list, as an ID column, and also capturing the row names of the matrix, which is the source region sector. And the columns of the matrix will be turned into data frame columns by this unlist2d function. And I can return also a data table by specifying dt equal to true. And then I can call data table's melt function to just turn this into a long form data frame. So grouping objects are really a great way to outsource group computations in R, and they're also the most general way to do that because they provide lots of information that can be used for lots of different algorithms or group statistics to perform without needing to make any new hash tables or anything like that. But there's a downside to it, and the downside obviously is that they cannot be subset, and they cannot easily be added as a data frame column or so. It's really an object of its own, and that can be a limitation. And base R has an object, the factor, which already provides a lot of information about a grouping or about which rows of the data are of the same group. And Collapse was designed to make direct use of factors as well. And there's also, for that, there's first a function that can be used to create factors very efficiently from integer or character or numeric data, which is the QF function here. And yeah, that is even a bit more efficient than grouping with group. So here you see, for example, I have, again, 10 million observations, 1% missing. Here I have, again, 1 million random integers defining groups. So the vector is also length 10 million, but it has 1 million random groups. So grouping this with group takes about 0.16 seconds. And yeah, if we converse this to a factor with QF, this is a bit more efficient. And what you can notice here is I've set an additional argument here to QF, which is the NA exclude equal to false. And that is basically the same as if you take the base R function factor and you convert this to factor and you put exclude equal to null, which basically means you assign a level to missing values. And this has the advantage because the vector can be used, or the underlying integer vector underlying the factors can be used directly in C++ without the need to check for any missing values, because a missing value used in a grouped computation would cause basically a seg fault and would cause the program to terminate. And Collapse ensures this by adding an additional class here if you set the NA exclude equal to false. So it has a class factor and a class NA included here, which allows any checks that would be executed inside a Collapse on a normal factor. In particular, there's a call to the any_NA function to check for any missing values if the factor does not have the NA included class. And this check can be skipped by putting this here. And in particular, I've just shown you here the internal Collapse function that is used to check factors before they enter into statistical algorithms at the C or C++ level. And it just checks if it's a factor, and then it checks if it either inherits this class, so a factor, or if it was generated in this way, or if it does not contain any missing values. And if this check fails, then it will have to add a level for the missing values in the factor, which is a bit more expensive. So here I give you an example, again, just aggregating this 10 million random normals over 1 million groups using here just the integer vector, which is non-grouped. So this will be internally converted to a factor. So it will internally execute this up here. And you can see that really adds to the execution time. So it takes many times longer than it would have to take. Then you can see here with the grouping object, which is very efficient. And yeah, especially if we do not skip missing values, which means because the grouping object contains, if you remember, it contains the integer group count, so we don't need to count the number of observations in each group, which gives additional efficiency. But you can see here that the factor f here, which we generated here with NA exclude equal to false, is also quite efficient, or it has the same efficiency as using the group object, because for this particular statistic, the mean, we only need the number of groups, which is the same as the number of levels of the factor, and we need an integer vector showing which row belongs to which group, which is provided also provided by the factor itself, or by the integers underlying the levels. So this gives exactly the same computational performance. But that is not the case for all statistics. For example, for modes or medians or so, the grouping object will be a bit more efficient than the factor, because there has to be some additional things computed if you pass a factor to these functions instead of a grouping object. But you can see here also that this, if the factor does not have the NA included class, which is the case here for F2, where I just only set the factor class, you can see that adds a little bit to the execution time, because I have to first run once through the factor and check if there's any missing values. And here, this is just for your interest. I talked a bit earlier about the F1st with NA remove equal to false that could use the group starts argument in the grouping object to just do a subset here, and you can see that this can be extremely efficient even on large data if we just want to take the first value in each group. Now there's one downside of factors as well, and that is that their generation can sometimes be expensive, in particular if the vector you're turning into a factor is numeric or is a date time object or something like that, because factors are only valid if the levels have a character type, and the coercion of a numeric or date vectors to character can be quite expensive. And because what we only need from a collapse perspective, really for computations, is the number of groups or the number of levels. We don't need really the levels itself unless we want to attach them as names or row names. So collapse provides another object, which is a kind of factor light, or I've called it a quick group object, and it has a class QG, which is again the same as the generator function here, and that can efficiently create a QG object. And the QG object basically looks like that. It just has the integers, which are the same as the integers underlying the factor, but instead of a levels attribute, it just has an attribute called n.groups, which just provides the number of unique groups in this vector, and it has a class QG. So so if you recall here, G is just an integer vector here. We could also turn G, knowing that we have knowing that how many groups we have, we could also turn it into a QG object by just assigning n groups equal to the number of distinct values here, and adding the classes QG and also NA included for the same reason as for the factor, to skip any missing value checks. So you can see here, that these two give equivalent computation speeds also to the factor. One thing to note is that QG also sorts the data. So as I said, the default in collapse is really to do ordered groupings. So just like QF, it will sort the groups as if there were levels to be sorted. And that can, once the object is created, that doesn't really matter for computation speed, as you can see here. If you do the sorted version, or we just turn the raw random vector into a QG object. It doesn't really matter for execution speed, but the generation can be faster if you don't sort. So you can set the sort equal to false in QF, QG, group, and also in the higher level functions like fGroupBy. And this will call a more efficient algorithm to group data in first appearance order, which is also available directly by a function called group. So this is just an example here where I just remove again the attributes from G, just turn this back into a plain integer vector, and then I call this group function directly, or I could equivalently, I could call QG and set sort equal to false. So you can see that this is faster than the sorted grouping, and it can be a lot faster with character data, where you would need to do some alphabetic ordering otherwise. So collapse also internally, if you don't pre-group data using group or factor generation or QG objects, it also makes some use of that, knowing if data needs to be sorted for a certain computation or not. So here this compares basically, so again, we remove the attributes here from G, so it's a plain vector. So both of these calls here do an internal grouping, and this one just computes aggregate statistics, but this one transforms the data, or it expands the aggregate statistics again to the full length of the vector. And curiously, you see that the latter one is faster. But knowing what I just told you here about sorting, this should be explicable, because in this call, collapse knows that you are expanding the data anyway to the full length, and therefore the grouping does not need to be sorted, because you're never going to look at the output at the aggregate statistics. So it does an unsorted grouping here, which is why this overall expression is faster than the one here, where we are returning a summary statistic, where we by default do sorted grouping. So that's good to keep in mind if you really want to push code or optimize. So here I'm just going to give you a sort of high-level summary of the different functions and algorithms for grouping and ordering available in Collapse. We have group, which is for multivariate data and returns this list-like object of class group. We have QF and QG, which return either factors or quick group objects. We have F interaction, which also returns a factor or QG objects from multiple vectors that can be passed to it. And we have F drop levels, which is just a very fast way to remove unused factor levels. Because if you have many unused levels in a group, in a factor, and which you don't need, it can also add to the execution speed. Then all of this is powered by basically two functions. One is radix order, which does ordered grouping or ordering and ordered grouping, and then the group function, which does the first appearance order grouping and also returns a QG object. And again, group works with, or both of these work with multivariate data. We also have two programmer functions to basically split vectors using a group object. You can also use factors, and so they will be converted to group. There's a few S3 methods for the group function to convert factors and QG objects to it. So this is much more efficient than the base split version, even if you just use factors. But it's very efficient if you use group objects directly. And then once you have split, you apply the function and you unlist the result again. And if the result has the same length as your original vector, you can use gReorder together with the group object to make sure that the elements are ordered in the same way as they were in the original vector. And then we have some also more specialized functions. We have a function which is called group ID, which I think is a bad name, but it was created before some of these other functions. But basically what it does, it generates a run length type group ID. And it can do this also using a different ordering. So it can by default it just does the run length type in the first appearance order of the groups, but you can also pass an ordering vector to it to pass through the data in a different order. Seek ID is a bit more specialized. It just groups integer sequences. So sequences of 1, 2, 3, and 4, 5, 6 or so, they will receive the same group ID. And time ID is a function that will become more important later on, which is just for grouping of time sequences. And what it basically does is, if you pass, say, a time vector like a date vector or a year month vector or so, it will determine the greatest common divisor of the data, and then divide basically the data by the greatest common divisor and make sure that the minimum takes a value of 1. So it will group the data assuming that it's a time variable, and it will preserve any time differences between different periods in greatest common divisor steps. Then apart from the fast statistical functions, there are also a number of other functions that are useful. First of all, if we want to just use some base R function like the quantile or the interquartile range or something like that, we can use either dapply or by. So dapply will apply a function to rows of columns of a data frame or matrix, and by just works basically like the fast statistical functions, but it applies column-wise, it applies functions by groups. But you can use it with any R function, and it's also very efficient. Like it's comparable to the efficiency of data table with base R functions. Then you have some specialized functions mainly for panel data, like F between and F within. So if you come from panel data econometrics, you know these are transformations, or also known as centering and averaging data over groups, which can be a bit more efficient than F mean because they don't materialize the aggregate output. And then FHE between, FHE within are when you want to center panel data on multiple vectors or factors. And these are actually internally powered by a fixest, which is another great package for panel data. Model fitting. And you have scale, which can do scaling and centering, including group level scaling and centering and harmonization of data. And finally, you have a set of time series or panel series functions like cumulative sums, lags, differences, and growth rates, which I will talk about later. Then Collapse also provides a set of data manipulation functions, which are principally performance improved versions of BaseR and dplyr functions. They mostly work equivalently, but they have some small differences or improvements. Particularly, you also have some versions of functions that have a set, start with set, and these also modify data by reference. One of the important functions here is fGroupBy, which creates a class agnostic group data frame. So here I give you an example where I convert this empty cars dataset into a data table, and then I group it here and select some variables, and then I do a grouped scaling operation on these. And you can see it's still a grouped data table, and all methods of data table really apply also to this grouped frame. So in that sense, it's quite flexible and also provides you some more advanced statistics here on the number of groups, and here some statistics on the group sizes, the distribution of group sizes. And just to say, this grouped fGroupBy, this group data frame is implemented by basically attaching a group object to the data frame. So why did I create these data manipulation functions? Well, I want to facilitate working with the fast statistical functions and so on, and data manipulation tasks, and also because they are really efficient in terms of just the basic code execution speed, because I only use a primitive and internal base R functions, and I do many checks at the C++ level. That's why they are very, very efficient for programming. So this is just a basic expression here that I'm comparing with collapse. So I'm converting this to a tibble to just make sure that there's no conversion also with, or there's the same conversion also with dplyr. And I'm also here, for data table, I'm converting it to a data table. And then, I just subset the data, I compute a variable, I group it, and I summarize across, I think, 5 columns here. And then I reorder the result. And here I use actually the base sum with collapse. And here I use fsum. So fsum could also be used in an across call, and it would optimize it perfectly fine. But the most efficient way to code this is, for example, to first of all use fsubset to subset both rows and columns, and then to just group the data and just pass it straight to fsum, which has a group data frame method, and then reorder the result. So you can see that, with this small data, this does not make a huge performance effect, but with larger data, trying to use efficient collapse syntax can make a difference. But you can see that both of these calls are about 3 to 4 times faster than the data table call, and many times faster, like, 40 to 50 times faster here than the dplyr call. So there's a lot you can do also with collapse, just if you want to write code that executes very efficiently. And I would even go so far as saying that the smaller your data becomes, the faster collapse will become relative to dplyr and data table, because the functions really don't have any overhead at all, or any really constraining overhead at all. Now, to talk a little bit further about how these functions integrate with the fast statistical functions and also the transformation functions. By the way, let me just say something here. So these transformations and time series functions, they have a syntax that is very similar to the fast statistical functions. They also have a G argument. They also have a weights argument. They just don't have a tra argument to sweep statistics out, because the output of these functions by default has the same length of the data. But they have some few specialized options to give different kinds of transformations. So the architecture otherwise is very much the same as the fast statistical functions. So here I'm just giving you some examples. So here we can use f transform, which is just a faster version of base transform. And you can see here that the simplest way, for example, to compute a column that is the sum of some column by some group is just to use fsum directly, to not do any groups. The thing with f transform is it does not operate with group data. So if you group data with f group by, it won't affect f transform. But what you could do if you're using the Magritte pipes here is you could fetch the grouping object using group, which also has a method basically for grouping, for group data frames, that just takes the object attached to the data frame and returns it. So that could be this. But then there's a mutate, of course, which is much more sense here, that works with the group data frame and will give the same result here. Why I show this is because I just want to tell you that what is happening here in fmutate, if you pass a fast statistical function like fsum, is it will be internally translated to something like this, which means the group object will be taken from the data frame. It will be passed to the g argument of fsum, and the transform argument will be by default set to replace fill. So basically this call is just captured and some other arguments are added to make fmutate work with these fast statistical functions. So knowing this, you can also specify different transform arguments here. For example, if I want to divide this variable by its grouped sum using fmutate, I could also just pass the char argument equal to the division operator. So if I specify an alternative transform argument here, it will not be overwritten by the default setting in fmutate, which is replace fill. So you can optimize this call here just by putting this here. Another thing you should note about the way these expressions are evaluated is that the execution is vectorized, which means that the syntax is translated to something like that and then evaluated whenever there is any fast statistical function in the expression. And Collapse doesn't care what other functions might be called in that expression. Whenever there's a fast statistical function, it will be the fast statistical function expressions will be translated and the others will be kept as is. So this actually here does not give a vector of ones. It computes the grouped sum of MPG and it divides that by the overall sum of MPG, because this whole expression is vectorized. So you can imagine it will be equal to this divided by some MPG. So that's something useful, I think, but it's something to keep in mind. Now f-transform ignores group data, and but it has an additional feature, which is that it can also you can also input data frames or lists in it, and it will be the same as like a comma separated set of compute expressions. And this means, at least if we're using the Magritte pipes, that we can run a pipeline inside f-transform. So we can group the data here, then we can f-select these columns. So this preserves the grouping, and we can then call f-between, which will average the data by groups. Then we can ungroup it, and then we could still call an f-sum here, and we could divide. So this basically just scales the data by the sum. So it turns it into proportions. And the f-transform here will, after this is computed, which is inside, it will just replace the columns HP through QSEC here with the shares that I've computed here. So you can see here really that these two here are equivalent. I can run it as a pipeline inside f-transform, or I can call the mutate with across. So it depends on what you like more, or if you want to do more complicated things, maybe f-transform will be more, you will be a better choice. Another thing here is we can not only add a different transform argument in fmutate calls, but we can also use a set argument to do data transformation by reference. So what this does here, it groups the empty cars data set. We apply fsum across these columns, and let me also just note here with an across statement. By default, Collapse will call the data frame method. So that gives you an additional speed because you don't need to apply fsum over the subset of columns. You just use the data frame method. So here we are scaling this. We are turning it into proportions, and we're doing this by reference. And we could call invisible here if we don't want to see an output, because our data frame empty cars will just have been modified. But note that the data is modified by reference, but it will not be grouped, because the grouping does not happen by reference. It's just the transformation of the data that is by reference. So the shallow copy of empty cars that is grouped, that was used to compute this, will be lost in this expression, but the data will be modified. And the final feature that I've added in both fsummarize and fmutate is that you can, in across statements, you can set apply equal to false to basically apply a function over a whole subset of the data. So here I just compute pairwise correlations of the subset, and then I turn this back into a data frame. Yeah. So that's what I wanted to illustrate a bit about how these data transformation functions integrate really well with the fast statistical functions, and also what to keep in mind there. It's important that apart from fsummarize and fmutate, all other manipulation functions ignore group data, which does not mean they drop the grouping, they preserve the grouping, but they don't interact with the grouping in any way. For example, you can't group data with collapse and then reorder it or something like that, because that will just reorder the rows of the data, but it will keep the grouping object the same. So it will give you a wrong result. You should always first reorder or subset data and then group it to get, because that is also what makes computational sense. So that is good to keep in mind. There's a couple of other functions which I just thought are useful to just here select columns or variables using indices or regular expressions. We can just add columns to a data frame by just assigning them when we wrap addvars around the data frame. And what I thought was very useful is a set of functions to select and replace columns by data type. And these are really based on C code to determine the type of variables. So they're much more efficient than using, say, sapply data is numeric or sapply data is factor or something like that to determine the types. These are some other programming functions which I thought are just useful to mention, which you've already seen. Collapse provides very efficient converters, just to convert matrices to data frames, tables, or tibbles, or to lists. Or you can also convert a matrix to a list, either row-wise or column-wise. So these are very, very efficient converters in case you do need to convert data types. And they are also accurate conversions. So by default, they will drop any redundant attributes to the data. We also have some efficient utilities like multiple assignment operators, which are also programmed in C. So they are also much more efficient than solutions provided in other packages based on R code. We have efficient functions to deal with variable labels, in particular V labels, fetches or assigns labels to data frame columns, also based on C code. And we can have functions to just copy attributes or remove attributes from data without any checks. So they're also very efficient. And we also have a very efficient function to determine unique values or unique rows, or the number of unique rows. And finally, this .c, which is just a convenience function, which you see often. It just takes, you can just basically create a character vector without quoting the elements in the vector. You can just write them out as code, but it will quote them basically for you. And there's also a number of functions to make programming in R more memory efficient. and particularly where you can check if of any or all elements of a vector are equal to a value or missing. You can do a comparison between two vectors or a vector and a value and return indices directly, which can be much faster than just returning a logical vector and then turning that into indices using the which function. You can copy elements from vectors, from equally sized vectors or data frames by reference. And you can also replace a value in a vector efficiently using the setv function. Setup allows you to do math by reference which is very general. It basically works like base R math, column-wise by default, between vectors, matrices, and data frames. But you can also do row-wise operations using the setup function. So this is very efficient for math. And then you have functions to do fast removal of missing values, faster checking the length of elements in the list, faster range function, faster dimensions for a data frame, and so on. So these can really speed up your programs at the micro level, and I use them often. So now that I've really introduced to you the statistical functions, the transformations, so the grouping elements and the data transformation functions, I want to walk you through an example from my work involving OpenStreetMap, which sort of brings these elements together. So the work here is a work to evaluate the effects of road quality improvement on local economic activity in Africa, on the whole continent using OpenStreetMap. And the approach that I'm investigating here is to study the growth of OpenStreetMap in the neighborhood of roads that have been upgraded. Because OpenStreetMap, of course, not only provides information about infrastructure, it also provides information about different kinds of features like shops and restaurants and so on. I want to see how these relate to economic activity. And to do this, really, I have generated a set of. I've divided the features of the map that are not roads into 26 different categories, and I've assigned a weight to each type of feature depending on how closely this relates to, or this type of feature relates to aggregate economic activity, which I measure with some geospatial outcome measures like Facebook's relative wealth index and so on. So here I just import the data, which is saved as a QS file. So this imports the features near the roads, and I take the whole history of OpenStreetMap in Africa from 2010 to 2022. This here is a list of nearest features to the roads, which basically for each road it gives the nearest features, but we will see it a bit later. And this gives two sets of weights, which I'm also going to talk about more later. So what this does here, it just aggregates the features data frame to a monthly frequency. So because it's a history, it's an OSM history file, so every change in a feature is recorded. And I want to remove sub-monthly changes, so where a feature changed 2 times within a month, or a feature appeared in a month and disappeared again in the same month. So therefore I'm putting the valid from and valid to columns, which give basically tell you when a feature was added and when it was removed or changed. I coerce this to year-mon variables using from the zoo package, and then I take the unique values here on the OSM ID valid from and valid to month columns, and then I also subset. I remove all the observations where valid from is greater or equal to valid 2. And then I group this by OSM ID, and I just take the mode of the category, which tells me what kind of feature it is, because for some features which all have a unique ID, the type basically can change, which is rare, but sometimes it does. So I take the most frequently assigned type here, and I take the minimum valid from the maximum valid to month, and I convert this to a data table. So this is how my processed data looks like. I have an OSM ID which identifies the feature. I have the category here, like shop or school, and I have the valid from and the valid to, which gives me basically the month the feature first appeared and the month where it was finally phased out. And you can see here, we have in total this data frame has 2.7 billion rows, and we have 26 categories and 144 periods from Jan 2010 to Jan 2022. And you can also see that here, where I selected these columns and I applied the range or the fRange function here to show you. Valid from goes from Jan 2010 to December 21, and valid to goes from Feb 2010 to Jan 22. And then here this shows you the nearest features list, which I just show you the first elements from the list. So the names of the lists are the different roads I'm considering. And in total there is about 67,000 roads. And then the content is basically all features or all IDs of features that are within 25 kilometers from the road. So this is something I've done before. Before importing this data, I've matched all the roads to all the features from these 2.7 million features that are within 25 kilometers of the road. And so these are named vectors. The names are the names or the OSM IDs of the features, and the value is the distance in meters to the road here. So this is how this looks like, and you can see here, if I calculate the length of these list elements, you can see that there's a variable number of nearest features to the different roads. So it goes up to roads where you have no feature at all that is within 25 kilometers of the road, in any portion of the road. So very remote roads in Africa. But you also have roads where you have lots of nearest features, like 88,000 nearest features. And then you have a set of weights here that reflect the contribution to each feature to local economic activity, which I estimated before using geospatial data. So here I'm just giving you like the first 6 elements of this parametric estimate, which shows you that, for example, marketplaces have a quite high or have the highest economic activity weight, followed by a line, which is something like telecom infrastructure, gas stations, other amenities, which is like things like cinemas and so on, universities, and alternative, which is some other higher forms of education, or things like driving schools and kindergartens and so on. So here you see some summary statistics of the weights also. So quick summary is also a collapse function that efficiently computes summary statistics. So now the next step for me is to create a timeline here from Jan 2010 to Jan 2022, just as a year-month object. Which has 145 periods in this case, because as you recall, the valid from goes from Jan 2010 to December 21, and valid to goes from Feb 2010 to Jan 2022, because I made sure over here that there is no valid, or that the valid to is greater than the valid from. And now what I want to do is the following. Basically, I want to create a measure of a time varying measure of economic activity in the vicinity of each road. So I want to aggregate over roads the different features that are present in every month, using the distance to the road and also using the activity weights of the different features to the road. And I do this with collapse in the following way. First of all, I generate a QG object of the valid from month and valid to month variables using the time ID function, and then I just set the n groups attribute, but by default is 144, because again the beginning, this one starts in or this one ends in December 2021, and this one starts in Feb 2022. So they have by default the attribute is 144, but I just increase this to 145 periods to make them consistent. And I also add here, by reference to the valid 2 month, I add 1 to make sure the underlying integer vector is also consistent with the valid from month vector. And then I use here 3 sets of weights. I use just unit weights, which will mean I don't weight different features differently. I weight them all the same. Then I use the parametric weight estimate, where I just use the parametric weights, and as you remember, this is here a named vector with the names corresponding to the different types of features, and we have 26 different types in total. And then I index that by the category column, which as you see here is also a character column with just a different features. So basically this just adds a column to the data set corresponding to the weight of each feature category. And I do this for the parametric weight estimate and also for the non-parametric weight estimate. So this is how the features long data frame looks like after applying these transformations. We have these valid from months. So you have November 2010, which is 11 here in the QG object, because the first month is Jan 2010, and August 2015 is 68 here, and so on. And Jan 2022 is 145. We have the unit weights, the parametric weights, again corresponding to these feature classes here. For example, the school has a weight of 1.79. And then the non-parametric weight estimate, which is a little bit different. So now, for moving towards the computation I want to perform, I create a list of these columns I want to use for the computation. So the 2 QG objects and the 3 weight estimates. I just use subset, which is a base R function, to create a list of these columns. Now, there's one thing I need to do, and that is I want to efficiently get the features from, or the rows, let's say, from this long data frame corresponding to the nearest features of a certain road. So what I need to do is I need to do a large lookup that gives me the indices of the rows of this data frame corresponding to the IDs that are nearest feature to a certain road. And the way I do this here is using a package in R called fastmap, which allows you to read things into a hash table and then to retrieve them, again, efficiently. So I create here a fast map, and I put into that fast map basically the row numbers here, which is just the 1, 2, 3, and so forth. I just have a list, which is a list of row numbers, and the list is named by the OSM ID column. And what I then do is for each nearest features, and if you recall again, this is a list for each that provides for each rows the nearest features as a named vector of distances. I just retrieve the names of the I retrieve the indices of the nearest features in this data frame using the names here. So if I have the indices, I can get the subset of this data frame, or in particularly of this FLL subset of the data frame much more quickly. And you can see that this lookup takes a lot of time. It takes almost a bit more than a minute. But yeah, the fastmap solution is here very efficient compared to using something like base match or in all the time. And then what I finally do here is I create, I take the 3 weight vectors. I just create a vector to call W which just contains the names of these 3 elements. And now here I perform the aggregation, which gives me the feature and distance weighted economic activity measure in the vicinity of each road. So what this function here, which I call doag, does, it takes x, which is just each nearest features vector here, each element of this nearest features list, which gives me the distances of the features to each list, and it gives me the indices of the of those nearest features in the features long data frame, or in particular in the FLL subset of columns, which gives me the activity weights and also the valid from and valid to variables, which will show me when was the feature added and when did it disappear again. And this, what I just do here is I just remove, in case the distance vector is empty, there's no nearest feature to the road, I just return null. And here I also remove any indices which might be mismatched or so. And here I just unlist the indices to make sure I actually get a vector of indices. Then I do distance weights. I turn this distance in meters x, again, which is here just a vector of distances in meters. I turn this into a weight by saying that if the distance is 100 meters or less, I just assign it a weight. I just assign it to 100, and then I just say x is equal to 100 divided by x, which means that features that are 100 meters or closer to the road receive a weight of 1, and all other features that are further away receive a weight that is smaller than 1, depending on the distance. Yeah, so the larger distance, the smaller the weight. Then using the indices I have here, I can efficiently subset the features long list here, which again just contains the valid from and valid to month QG objects and the 3 different weight estimates. And what I can then do is I can use these weight estimates, which are contained here and which I retrieve here using the names of the weight variables, which again are just the names here. I can aggregate this over the entire period using the valid from grouping here, which I also subset here, but because the ngroups attribute is also a subset, it's going to be 144 elements in the output vector. So it's always going to be that 144 elements, and I'm going to sum these different features according to their weight, and I'm going to sum the weights into the period when the feature first appeared. And I'm also going to weight all of this by the distance weight. So this does a doubly weighted aggregation using the different activity weights and also the feature weights. And it will output here just a list with 3 columns, like the 3 input columns, but 145 periods, which is just the number of periods we set here in the so it sums the entire weight basically into the time the feature first appeared. And now there's still a problem, which is some features may disappear before the end of the sample period. They may disappear before Jan 2022. So, and if that's the case, and I'm checking for that here, if not all values valid from 2 equal to ng, so if not all valid 2 QG elements are 145, so if some of them are not 145 or smaller than 145, I also create another result where I do the same thing over the valid 2 QG object. So it's also going to be length 145 with 3 columns, but it's going to sum the entire weight into the period or the row where the feature was phased out. And what I then do here is I lag this list by 1 period and just put a 0 in the first period instead of NAs, which would be the default. And I subtract this by reference from the original list. So basically I remove the weight again 1 period after the road was, or the feature was phased out. And then to get a correct timeline of the total feature weighted and distance weighted economic activity in the vicinity of each road, I cumulatively sum this whole thing. Yeah, so we add the weights in the initial period. If some features disappear before the end of the sample, we subtract the weight out again 1 period after they've been phased out, and then we cumulatively sum everything to get a consistent timeline. And I also add the timeline variable here. So and this gives you the way I apply this. I just use a map call here of doag, putting in the nearest features, which gives me the axis here, basically the distances in meters, and the ind list, which gives me the indices of the weights and time list here. So we have in total, let me check it again, the summary statistics, but we have, we have 69,961 roads. And for each road, we do this thing, we do this doubly weighted aggregation over time, and we generate basically a list with 3 columns and 145 elements. So all of this using collapse and using the fact here that these are QG objects, that means that there does not need to be any grouping happening in these fsum calls. The grouping has already taken place. It's just always going to be those same 145 periods. This whole function is extremely efficient. Yeah. So this whole 69,000 roads here, doing this for each road, the doubly distance weighted aggregation just takes 6.9 seconds, and I calculated that's approximately 80 microseconds per road. And then as a final thing, once we got this roads activity data frame, We can rbind it using data tables rbind list function and set the order again. And this is the result, right? So we have for each road, we have in each period, we get a total weight which reflects the economic activity in the vicinity of the road based on the types of features that are around the road and the different activity weights assigned to different types of features, both using a parametric or non-parametric estimate, and also the distance weights of the different features to the roads. Yeah, so this is a very complex operation, and like without packages, I think like Collapse and FastMap in this case, it would not really be possible to do this in R in that level of efficiency. So yeah, so in the last part of this talk on Collapse, I will introduce a bit the time series infrastructure offered by Collapse. Which I think is really a contribution to the R language in terms of both the way it can handle time-aware computations, taking account of irregularity and so on in both time series and panel series, but also in the terms of the performance and also the flexibility with which different kinds of time series and data objects can be handled by it. So here I give you an example of just a time series that is available in R in the datasets package. So it's an air miles time series, and just giving the total air mileage, I think globally, and this just computes the growth rate of this time series. By default, this will just put a missing value in the first period and have the growth rates of this annual series for the other years, 1937 to 1960. Now, to showcase a bit what Collapse can do, I just add some gaps into this time series. So here I just sample randomly 5 observations, and I remove them from the air miles time series, and then I also take the time of the time series object here, and I also remove those indices here, and I just group it basically, or I make it a time ID, and then I can compute the growth rate again on this, which is now a vector, because removing or subsetting a TS object unfortunately removes the class. So this is just a plain vector, but we can still index it here by this time vector here, and you can see that f growth took account of this now irregularity in the data, and so in parts where there is a gap in time, you also get a missing value here, and the growth rate is not computed wrongly here. And so collapse time series operations are very general. So for example, with the growth functions, we could compute the growth rate here with multiple lags. We can compute a leaded growth rate, and just the normal 0 just gives the vector itself, and then we have growth rates on 3 lags of the data, and you can see here where there is irregular gaps in the sequence, it will propagate the NA here, so it will not run a computation. And here actually I also compound the growth rates to quarterly growth rates. So this is just one example of like how general this framework is. I'm just giving you here also another example using differences here of the EU stock markets time series, where I just generate a sequence of 1 leaded and 1 lagged differences, and I also use first and second differences here. So for example, this is the leaded first difference and the leaded second difference. This is just the data, and then we have the first and second difference. And then here we have the first and second leaded difference of the other index here, and so on. So this is for time series. You can also use this with data frames, obviously, and also with panel data frames. So here, for example, I transform a data set called WorldDev, which is provided in the package, which just gives some indicators on the development of different countries over time. So here I take the GDP per capita, the life expectancy in the population, and I compute the 1 and 10-year growth rate of this panel data. And I supply here to the G argument of f growth the individual dimension, which is the country code, and the time dimension to the T argument. And I just call apply equal to false to make sure that the data frame method of f growth is used. And in this case, yeah, it will generate new columns containing just the growth rate or the lag 10 growth rate. So the 10-year growth rate of each of these variables. And then, yeah, you can also do this with panel data, which has multiple ID variables. For example, this is another data set provided in the package, which is data on structural change, which has a country and a year variable, but it also has a variable column which provides two different measures, value added and employment. So you can also compute here on these, which is sectoral data. Now I can compute on these sectors the 10-year growth rate, and I can group by variable and country, and also identify the time dimension by the year variable. And here I'm also doing some compounding. So this is just an example in terms of what you can do. Just ad hoc, basically using these functions combined with some data manipulation functions. So Collapse also supports indexed computation on indexed data. In particular, it supported from very early on the PLM, linear models for panel data, packages, P-series and P-data frame classes. But recently in the version 1.8 and onwards, Collapse has introduced own classes for time series and panel data, which are called indexed series and indexed frame. And these are really very general classes because they can basically be imposed on any kind of data frame or matrix-based object without interfering too much with the functionality otherwise of the object, but they provide the possibility to do time-aware index computations on these objects using Collapse. So here I'm giving you just an example. I'm just pulling out from this world development data set the data for Germany from 1970 onwards, and I'm just taking these four variables: the year, the GDP per capita, the life expectancy in the population. And here I'm just randomly removing, as is a shorthand for subset, basically, I'm just randomly removing two rows, which is the second and the fifth row. So I'm introducing some artificial irregularity here. And then what I do is I index this data by year. So here this is the findex by function, which just indexes this by year. And then if I print it, first of all, you see the irregularity here. The 1971 period was removed, but otherwise the data is still a data frame. And then you can see the printout below. It says indexed by year, and we have here 49 periods present in the data from 1970, I think, to 2019. But in total, it should be 2021 actually. In total, there are 51 periods. So 1971 to 2021 will be 51 periods, but we only have 49 periods that are actually present in the data, because we randomly removed those two. So you can see that the indexing already detected sort of that the sequence that we have here in terms of time is longer than the actual time values that we have in the data. And then we can compute also growth rates. And here I'm not using the f growth function. I'm just using the g operator, which I talk about a bit later, which just has the advantage that it preserves the ID variables, so here the year, without doing any computation on it. So it has a more convenient, it's a shorthand, but it also has a more convenient data frame processing. So here you can see the growth rates here, and you can see that we don't have a growth rate computed for 1972, principally because we are missing the 1971 variable, right? So we can't compute the growth rate, and this is taken into account here. So this index frame here can also be manipulated in any standard way using, for example, just the subset operator in R to take a subset of rows and columns, and it will still be indexed. So the index, the methods here for index frame, it will subset the index, but it will then call the method of the original object that you created, which is a data frame here, and then do the data frame subsetting and attach the index again. So the computation here also works fine on this object. There's also an f subset method here, which here I just take the two columns. I omit here the year variable, and I just call f growth because I don't need to preserve the year variable. So this also works, and you can see it is also still indexed even if the year is no longer present in the data frame. Now this also works if we pull out variables from the data frame. So here I just take the per capita GDP column and I compute the growth rate, and you can still see it is indexed, and you can also see the index information being printed below. And this even works for nested computations, or for example, here I compute the growth rate of the per capita GDP variable. I take the 1 and 10-year growth rate, which will generate a matrix with two columns, the 1 and the 10-year growth rate. And then this matrix, I lag further. I take the first and second lag. So that I get the lags 1 and 2 of the normal growth rate, and also lags 1 and 2 of the 10-year growth rate. And you can see that this worked perfectly, and it is still indexed. Yeah. So the matrix expansion here by f growth still preserved the index, and then f lag still performed an index computation on this matrix. So it's very general in terms of what can be done, and you can even subset like the per capita GDP vector. Just pull out a few observations and then still do a computation on it, the index will go along with it. Now, what is, I think, really remarkable about the way Collapse implements this in comparison to any other framework in R is that it works not even by pulling, say, variables out of a data frame and creating methods to subset index frames or index series, which also account for the index, but it also works within any data masking environment, right? So here the width function just makes all elements or all columns of this data set available in an environment where any function called in this environment can find them. So this is just a vector, and inside this environment it is not clear where this vector has come from, right? So it is there's no way for f growth to know that this vector came from an indexed frame. But as you see here, it still works. It still has the NA where there is an irregularity in the panel. So we still do an index computation here, and the result is also still indexed. And similarly, I can use functions both from any package, from Collapse, from dplyr, from data tables, from any data manipulation package, on an indexed frame and for example, perform computations here by adding a growth column to the frame, which is also a computation that happens inside a data masking environment without there being any kind of special methods created for F-transform and so on. And similarly, we can just use this inside formulas for LM. Here is the example, but it works with any statistical model in R with standard formula interpretation. We can do fully indexed computations inside that formula if we pass an indexed frame to the data argument. And you can see that this is an index computation, because if I remove the index, if I unindex the data, then this gives a different value. And yeah, so this also works for any package with the standard formula interpretation. Particular usage would of course be some panel data packages like fixest, LFE, or PLM. So for example, here I give you a fixest example where I index the WorldDev data frame by ISO 3 and year, and then I do an FE-OLS call here using the indexed growth rates of per capita GDP on life expectancy, and I take here the country fixed effects. So this works perfectly fine. And of course, fixest also has a way to internally do a panel computations if you specify panel IDs, but sometimes you want to do some prior manipulation, and I will show you also later that sometimes collapse can be considerably more efficient than the fixest solution on certain kinds of data. So again, this also generalizes to more complex panels. So for example, I can index a panel, for example, this structural change data here from the Groningen Growth and Development Center is a data where the individual dimension is identified by two variables, which are called variable and country, and then the year identifies the time dimension. And so fIndex expects the first variables to be variables identifying the individual dimension, and then the last variable is the time dimension. And you can see by default there is an interacted variable being created here for the individual dimension and then the time dimension separately. So this works perfectly well. You also have the option, or there's an argument to fIndex by where you can say you don't want to interact them, which can also have some advantages in some cases. So how does this work? So how is it possible to have these computations happening correctly inside any data masking functions in R? Well, first of all, when you index data, in a data frame of class index df is attached to the data frame, as you can see. And here, this one can be fetched just using the fIndex function called on any indexed object. And then you can see here the structure of this frame. And it basically contains factors in identifying the individual dimension and the time dimension. And the interesting thing about the time dimension factor is if there is any irregularity in the factor, so if there's missing periods, then it will include a level for those periods even though they're not present in the data. And that is a feature of the time ID function, which really considers the first and the last time point, and the time step is the greatest common divisor of all time points in the sample. So it will take account of any periods that should be there but are not there, and these are included as levels in the time factor. Now, if I fetch here from a column, so here again within this indexed version of the frame, I just fetch the agricultural column, which if you recall from here is just a column giving agricultural value added in that data. I can see it also or I can first see it's an indexed series and numeric variable, so all the other attributes are preserved. And it also has an index df attribute, but in that attribute you don't see an index frame, but you see an external pointer. And that external pointer points to the indexed data frame of the frame. And the nice thing about external pointers is that they work anywhere as long as the object pointed to is still in existence in memory. So they work in, you can call them anywhere, and they will fetch the object as long as the object is anywhere in your memory. So it's really not tied to there being a direct link to the series and the frame, right? You could even save the series in a totally different variable or different object, but as long as the index of the frame is in existence, this will work. And you can see that here, like if I, in this data masking environment, I call the findex function on the agriculture column, I get the correct index of the data frame, which is the same as here, which can be used for index computations. So I told you this can be this is also a class agnostic framework, so it can be superimposed on any data frame. Any data frame can become an index frame, and any vector or matrix can become an indexed series. So here I'm giving you an example. I'm just taking again the OSM roads data, the roads activity data frame generated, if you recall the OSM example I walked you through. I'm just turning this, I'm doing two things with it. First, I'm removing any zero weights, and this, in this case, turns this into an unbalanced panel. And I also add some random geometry. I'm just adding a point. I'm just adding a 0, point with a standard coordinate reference system here as a geometry, and I'm turning this into an SF data frame. So this data frame has 7.3 million observations and 6 columns. And here I'm indexing the frame, right? I'm indexing it by OSM ID and month. And you can see that spatial operations work perfectly fine on this frame, right? So you can get the coordinates of the features, which are just 0, 0. Here you can get them, and you can also do a spatial operation here, which here I'm just generating a within or a centered growth rate of the parametric weight estimates, which is quite fast, as you can see. And this is just an added column here. And you can see also here I can just subset this spatial data frame, and it will subset both the index. So you can see here, if I just take the first 3 elements, it's only one row left, and we only utilize 3 time periods, from which in total would be 145 periods here. Because again, the levels of the time factor are not automatically dropped, whereas the levels of the ID factor are dropped upon subsetting. So this is a full geospatial data or spatial temporal data structure. It has spatial information, and it has information of the time series dimension, and it can be used for either kinds of computations in R. And this just gives you an idea about how efficient this infrastructure is. So here I'm just unindexing this, and the unindex function removes basically the index data frame from the data frame itself, but it also removes the index series class and the external pointer from all columns in the frame. So here I'm just calling this roads SF for brevity. Here I'm creating a data table version, and I'm keying that on the OSM ID. And here I'm just I'm using another solution in R, which is the fixest panel, which which in this case takes very long to create actually the panel here, which I don't know quite why it takes that long, but yeah, it takes very long. But you can see here that the collapse index frame, or the indexing itself, just takes about 64 microseconds. So it seems to be faster in this case even than just keying the data table by OSM ID, and it's a lot faster, of course, than the fixest panel generation. I mean, I think fixest is slow in this particular example, but it seems to be taking very long. And so once this structure is created, and say when I compare this to the keyed data table and also to the fixed panel, and you can see really that the computation speed here of the lag, for example, the fully identified irregular panel lag of this 7.3 million observations with 69,000 rows just takes 29 milliseconds here. A data table, on the other hand, takes, first of all, it cannot compute a correct lag, because it does not take account of the time dimension. So because there are irregular gaps within each ID, so this is incorrect. But it also takes almost 10 times longer here, and Collapse actually has a way to do what data table is doing here. If you 2f lag or if diff and so on, you can put the shift equal to row, which will just shift the rows belonging to each ID without taking account of the time dimension. And you can see if that is being done here, we can bring the computation time down to 8 milliseconds. In terms of fixest, the computation is quite efficient once the panel is created. We have here 79 or 78 milliseconds, so it's a decently efficient structure once the panel is created. But of course the creation takes very long in this particular example, and it does not work inside arbitrary data masking environment. So Fixest has a particular method that allows it to work inside data tables, but it's a much less general framework than the index frames and index series solution, and there's also no indexed vector or matrix in the Fixest framework. But it's of course very nice to have if you just want to run a single panel estimation and the implementation works efficiently for your particular data. I just want to show also here, like this also works with the collapse SF frame. I can convert it to a data table and also do a data table based lags, although this QDT function in this case removes all redundant attributes, so it removes actually the index from the frame, but the series in the frame are still index series. They still have an external pointer, and since the Rhodes SF frame is in existence, that will still fetch the correct attribute or the correct index. So this also works perfectly well with collapse. So to conclude here, so the time series and panel series features of collapse, I think, are really a great improvement over existing infrastructure, both in terms of flexibility and performance. So we have several constructor functions here, also a function that can check if the series is irregular, and of course the time ID function, which is really useful to turn any time variable into an integer variable basically. Then we have the core time-based functions, which are flag, fdiff, fgross, fcumsum, which work on, they all have default vector matrix and group data frame methods, but they also have methods for index series and index frame to take advantage of this framework. And they also work with panel series and panel data frames. And then we also have PS matrix, which is panel data to array conversions. And we have auto and partial auto and cross correlation functions for panel data and panel vectors. We have then the transformation functions to scale and center data, optionally with using higher dimensional scaling, so you can also centering, or you can center data on all vectors included in the index, for example. And we have several data manipulation functions which do support indexed frames, so like f-subset, f-unique, row order, and na-omit. And this makes sense here because the index is also a data frame of the same dimensions as the data frame it is attached to. So in this case, we have a bit more broad method support, including reordering and so on. Although that is, of course, is not efficient and should be avoided. And we also have summary statistics on panel data, in particularly, which decomposes statistics or computes them separately on between and within transformed versions of the data. And we have the varying function here, notably, which checks if some data is variant over a certain dimension. So if it's individual variant or time variant and so on, which can be very useful to just analyze what kind of variables you have in your data. So that was the time series framework. I just want to talk now briefly about some syntax API extensions, really, I would say, of Collapse. And that those are basically, those came from a need that I felt that there should be a way to really a pilot code or do very rapid development and ad hoc use of certain functions without caring too much about whether this is very readable or it should just be efficient to code. So I have two kinds of function shorthands in Collapse. One is the statistical operators for data transformation functions. So for example, for the f-scale function, I have what is here a standardization operator. For f between and f within, we have operators b and w. For f-lag, we have operators l and f, f-diff d and d-log, and f-gross, we have g. So these are nice, really, if you want to use some parsimonious expressions, like in a subset call, you want to just compare a variable to a between transform or a group average version of another variable. You can use the b operator, or inside LM calls, as we have seen, the lag and the growth operators are very efficient. For the data frame method, these operators, they also have an advanced data frame method which can allow you to do basically ad hoc computations using formulas. For example, here you can create a lags 1 and 2 of the GDP per capita variable, and you identify the panel by the country code and the year variable. So you do a complete setup which contains all information necessary to run this computation just in a single short call to L. So this is I think a nice feature overall. And the second feature which goes in that direction is I just have function shorthands for data manipulation functions which I use very frequently, like select, subset, transform, and so on. And these are just obtained by compacting the main consonants of the these functions. So instead of fselect, we could just write slt or sbt or tfm or so, and that just allows me to write faster code, and you don't need to use it, but it's I think it's interesting also for group data frames. You can create them with gby, or you can index things with iby, which I think I also do here in this example here, which can just be convenient. So these are just part of the Collapse namespace. You don't need to use them, but they are there, and if you like to do rapid templating of code, I think that they could be useful for you as well. Now there's a second idea I had about namespace in Collapse, which relates to the observation that many of the functions here are of course faster version of existing functions. For example, subset and transform or base R functions, mutate and summarize, we know them from the dplyr package. Index by or findex are functions that we have in the tsibble package or the plm package. And it could be that I just want to use the names of these functions without the f or the fast version. Also for the fast statistical function, of course, we have fmean, fsum, and so forth. Or it could be the case that you have existing code written, say, using dplyr, and you want to really efficiently translate that to Collapse. And therefore, I've added you an option that allows you to export additional versions of these functions that do not have a leading f in the name. And that option is called Collapse mask. So to give you an example here, if you could set options collapse mask equal to fselect and fsubset, and that will mean once you load the package with this option set, you will have select and subset also in the namespace, which you can use, and they will work exactly like fselect and fsubset, which will also be in the namespace. And there's a few keywords that allow you to mask multiple functions, like manip, which masks all the data manipulation functions, or helper functions, or we can mask here the fast statistical functions, so we can replace base R functions like sum and mean and min with the collapse equivalents. Or we can put all to mask all functions. And the best way to do that, if you want to do this, is to use an R profile file in your project directory, or even in the user directory, so that the option is set whenever R starts, basically. So to just give you an example here, so if I set this collapse mask all here and I load the package, then you see that this here, which really looks like Dupler code here mixed with some base R, but this is really completely collapse running. Like, so even the fmean here, you can see I add a weight here, so this is clearly a collapse running, and it will be vectorized across groups, so it will be very efficient. And similar here, all of this sum, diff, drop levels, scale, unique, range, and so forth, lag, that's all collapse code. If you mask these functions. So that's pretty much it for Collapse. To learn more about it, you can consult the documentation, which I've also made an effort for you. Basically, you can load the package and then call help collapse documentation, and it will bring up this browsable table, and I will try to demonstrate this maybe shortly. Just like this, so we can load it and we can call help collapse documentation, and then we have a browsable documentation here, which is structured in a way first that this just gives the main summary of the different features, but we also have a topical summary here, which we can click, which just briefly tells you what each function does. And then we also have a table here which shows you the different methods that might exist for a function. And you can click on individual functions and so on. Or you can go back to the main table. And similarly, you can jump into every function, and every function that you call you can also go to see also, and it will suggest to you some closely related functions. It will suggest to you a closely related topic, or you can always go back to the overview page. So this is really a browsable thing. You can jump around here, but you can always go back to overview, or you can jump straight into related topics. So this is I think a nice feature. And another thing that exists is the website, which is sepcrunch.github.io/collapse, which also gives you the documentation in a similar way. It can also be browsed just like the built-in documentation. And we also have some vignettes, which I think some of them need to be updated, but so I think the main resource should be the documentation, but some of them can also be very useful, especially if you want to use Collapse with other packages. They provide some useful notes. So thanks a lot for your attention. So as a summary, I can say, just working as an applied economist, Collapse has really increased or pushed the boundaries of what I can do with R, and it made me much more productive in my research. And I think if you are an economist, or you are a statistical researcher, and you need to do complex things in R, and you need high performance, you need flexibility, you need advanced computations, I think you will really enjoy working with it. And in terms of the API, I think it is stable now. I'm happy with it. I don't have any plans to change it. And the package will receive further development in the coming years and months, especially in the domain of multi-threading and data transformation by reference. So I think it can be expected that this package will remain and progress towards the highest performing packages in the statistical computing domain. So I already showed you the website. There's also a GitHub link, and I also have an associated Twitter account where I share things about updates, basically, what is new in Collapse. So if you're very interested, you're very welcome to follow this.